Okay, so these equations give displacement, velocity, and acceleration as a function of time, but we can join them together in different ways to get rid of the time. So here's velocity as a function of displacement. So v here is a velocity in meters per second at a particular displacement x. Omega is the angular speed or angular frequency in radians per second. Capital A is the amplitude, the biggest displacement from the equilibrium, and x is the displacement at which we're trying to find the velocity. So let's say, for example, if we freeze this pendulum at this point here, this x, we know that it could be going towards the right at a particular speed, or it can be going towards the left at that same speed. So the solution there could be positive or negative. So it's a two-solution equation here. That's why we have that plus or minus at the front there. So velocity at particular displacement can be going towards the left or right. Okay, and let's take this function equation here and let's put in the maximum displacement, which is amplitude. If you put that in, you get a squared minus a squared, which is 0. So at maximum amplitude, at the very biggest possible displacement towards the right or towards the left, the velocity is 0, which is what we expect. Okay, at maximum amplitude, the velocity is 0. And let's take at equilibrium, where the displacement is 0. So if we put x equals 0 instead of a, then we get, if this implies to square root of a squared, which is just a, capital A. So we get an equation for the maximum velocity, which is omega A. So what would it look like if we plot this equation as a graph? So if we plot velocity against displacement instead of velocity against time, it looks like an ellipse like this. Well, why is it this shape here? Well, at a particular displacement, let's say, for example, in this case, I'm taking plus 1.5 centimeters, I'm getting two solutions. And this is because that plus or minus in front. The pendulum, the mass on the spring could be going up or down at this particular displacement. And similarly, in the negative direction as well. So if I pull it down by minus 1.5 centimeters instead of pushing up by plus 1.5 centimeters, I'd still get a positive or negative velocity as it goes through that point. Like other features of this graph, you can read the maximum displacement. So it's 2.5 centimeters here. You can also get, and at that maximum displacement, the velocity is 0. So you can read off that graph because when it says maximum displacement, it has to stop and turn around, so its speed going to equal 0. And then you can get the maximum velocity here, so it's plus or minus 0.8 centimeters per second, because and this is at the equilibrium. So if we read from this, you know that's at x equals 0, and it could be going in the positive or negative direction there. So here's an equation for acceleration as a function of displacement instead of time here. So acceleration in meters per second squared here, we've got angular speed, which is in radians per second, and that's being squared, and there's a negative in front, and then there's displacement in meters. This is consistent with a condition for superpower motion, which says that force is directly proportional to displacement and in the opposite direction to displacement. Because forces or resultant force is equal to ma, this is going to be proportional to acceleration as well. And if we plot this as a graph, acceleration against displacement, we get a straight line that goes through the origin like this. Okay, so with a negative gradient as well. From this graph, we can find the biggest displacement, in other words, amplitude, by reading off the biggest x value there. We can get plus or minus 2.5 meters. And at the biggest displacement, when it's displaced the most from the equilibrium, we get the biggest acceleration as well. So in this case, the maximum acceleration is 0.28 plus or minus meters per second squared, and that's also equal to omega squared A. Okay, another feature of this is because we plotted a on the y-axis and x on the x-axis, the number that's multiplying the number at the front, this is going to be the gradient of the graph. So the gradient is minus omega squared, which you can use to find the time period if you wanted using 2 pi over t. A simple harmonic oscillator is displaced by 1.8 meters and released from rest. So that's going to be our biggest displacement. So that's our amplitude there. The time period of the oscillation is 5 seconds. So that's our capital T. Calculate the velocity of the oscillator at a displacement of minus 1.2 meters. So that's the x that we're going to use. So I want velocity as a function of displacement. I'm going to use this equation here. Okay, so first I need the angular frequency here, omega. So that I can find using the time period, using this equation here. So the time period is 5 seconds. If I put that in, I've got my angular frequency. So I've got my plus or minus omega there. Square root of amplitude squared. So that's my square root of 1.8 squared minus the displacement we're looking for, in this case 1.2 meters squared. And so you can see the negative doesn't matter because when you square something, the negative won't have an effect. So if we put the numbers in, you get plus or minus 1.69 meters per second. So it could be going towards the left or towards the right, or up or down, depending on what kind of oscillator we have. The graph shows how the velocity of a simple oscillator varies with displacement. Calculate the angular speed of the oscillations in radians per second. So we're trying to find omega here. We'll look for information in this graph. One of the information we can get is the maximum displacement, in other words amplitude, which is 2.5 centimeters. We can also get the maximum speed, which is 0.8. So that's V max. Okay, so and that's in centimeters per second. Now, normally I would convert them, but in this case, because they're both in centimeters, they're actually going to end up canceling out because they're linked through this equation here, V max equals omega A. So I've got, all I need is omega there, so I can just put the numbers in and rearrange, and I get my answer. Okay, another way of doing this is actually just use any value from the graph and put it into the equation that we learned earlier on. So in this case, let's say I take 1.5 centimeters as the displacement and 0.64 as the speed, and I put this into the equation. Okay, and then I can get omega like this. This graph shows how the acceleration of a mass on a spring varies with displacement. A second mass on a spring oscillates with half the time period and the same amplitude. On the same axes, sketch a graph to show the acceleration of the second mass spring system. Okay, so firstly, with this one, the new one has got half the time period. So that's going to affect its angular frequency and its frequency. So if we use this equation here and we say that the time period is half, so at the bottom there times half, that means that angular frequency is going to be times 2 because it's inversely proportional. Okay, then we can look at the equation that links acceleration and displacement, which is A equals minus omega squared x. And we just saw that the angular frequency here is going to be times 2, but that's being squared. Okay, so if it's being squared, it's actually going to be times 4. And I showed you earlier on that in an acceleration against displacement time graph, well, the number at the front is actually going to be the gradient there. So the gradient is going to be 4 times steeper. So we can draw a line like this. But we can't just plot any arbitrary line. We need to make sure that it goes to the right points. So let's take a particular point on the old graph and make sure that the new gradient is 4 times steeper. So if we take an old point on the graph, the old line there, so we've got 0.28 and 2.5. So for 0.28, we should get a quarter of the value. So if we just take 2.5 and divide that by 4, and we get 0.63.